after 2012, there is a very big surge in, like, from last 11 years or so. Lot of people are talking about deep learning and all, and lot of interest is going high. But deep learning goes way back in 80s and 90s also, right? So I was talking to you about, I think in one of the initial videos, I talked about the the AI, like the overall umbrella term is AI. Inside that, there is machine learning and then there is a deep learning. But it has gone through these cycles, right? So there is this cycle of hype, and then there is this cycle of despair or something. I don't know, like what. Okay, or so what happens is that sometime there is some big breakthrough, and people think that okay, there is a lot of, like, AI will take you to the next level, and lot of research grants and a lot of industry has started investing, and all those things happen, right? So it has gone through two such cycles, and probably we are in the third one now. I do not know how high this will go, and or how not high it will go, but probably we are in the third cycle. So giving you a little bit of context over here, AI started in, I think I repeated this, in 50s, right? When in the Dartmouth and all those professors and mathematicians get together, and Alan Turing and all those people, right? They started working on that. So it started from 50s. But relatively in 80s and 90s, what happened is, was there was two school of thoughts primarily. Symbolic AI. The first one was called symbolic AI. The second one is called connectionist. Like there were two people, like two different type of people who believed in that how AI will come to life, right? So there were connectionists and there were symbolic people. Like the whole research world and industry was divided into two. What are like, and this was the broad division of AI. So symbolic AI people, they were thinking that every logic, like the way human brain works is that it has a way to figure out logic, right? Logical. If we are able to codify all the logical in the sense like decision tree type thing. So if this happens, then there are three options, and what people will choose A, B, and C based on what criteria. And if you are able to codify everything, probably will be able to achieve some level of artificial intelligence, like machine can start learning and mimicking human behavior. Okay, so that was the symbolic AI thing. Lot of research went, and at one point, symbolic AI was like people were thinking in 80s and 90s that this is the way to approach, right? And then in between, we also saw something called expert system, which was a sort of an offshoot of symbolic AI. Like, if I have to give you an example of expert system, like the fax machine in your offices, if you see, right, still the Xerox and all, like it has some intelligence, like the paper is stuck here and all those things, it will tell you, right? Those sort of systems which has some intelligence, like it tells you something, right, based on some graph or a tree of knowledge, were called expert system. Lot of people started believing in connectionists, and these connectionists were actually later known as, these are the people who started deep learning, right? So they were of the opinion that it's very difficult to codify all the human knowledge, like it is no way possible. So there has to be a different approach in which human mind thinks, and their approach is through what is called artificial neural network. So in our mind, we have biological neural network, or everybody, humans or animals and all the species have biological neurons. What they wanted to do was the artificial neuron, right? Lot of people started believing in this, but I think what happened over there in 90s and all, that all the hype around the connectionist AI also died down. Why it died down? Because it was promising initially, and then it didn't give lot of good results. Like uh, a society will only reward you if you are giving something back to the society which is useful to the society, right? Then it will give you a lot of money. So connectionist AI, although they were promising initially, they didn't, like, really created something which was very, very path breaking, which really changed the way the human lives, right? So like they didn't put the same impact as internet did or mobile phone did. Let's say, let me take two examples, right? These were the path breaking innovations, right? So connectionist AI was not able to do, and there are various reasons. One of the reasons could be that there were not enough compute available. And the second reason was there was not enough data available at that time. Okay. What happened? And so, okay, let me just, yeah, this is a, so what happened around, there was this particular gentleman, and you should see his videos on YouTube or whenever you are free. His name is Geoffrey Hinton, and he is a professor. He's not anymore, I think, but he was a professor in University of Toronto in Canada. He was a great proponent of connectionism, right? So he is known as the godfather of AI, and rightly so, because whatever we are seeing currently inside the field of deep learning has come out from him or from one of his students, right, in his lab. There is another person, French gentleman, lives in US, Yann LeCun. He is in the professor. He was the professor. Now he is VP in Meta or somewhere, but he was professor in New York University. Especially these two gentlemen, and these two gentlemen never lost the sight of deep learning or connectionism. They say that no, this is the way to go forward. When everybody in the world started disbelieving them, they had faith in their thing, and they kept working on that. This gentleman in 1996 or 95, maybe I may be wrong. What he did was, like how we have India Post right over here. In US, they have USPS, right? Their postal service. And the postal service had these handwritten digits on that zip code. We call it postal code. They call it zip code over there. And zip code is a 5-digit number, right? And now everybody used to write this 5-digit number. What Yann LeCun did, he worked with the department, this department, and he figured out a way to have the computer read these digits. And we'll see that today itself, that how and he used deep learning. At that time, it was not even called deep learning. It was called more like neural network or something. So he used neural network to read these digits and help solve the problem for USPS, right? So, and that was way back in 95, 96, right? Accuracy was also decent. It was better than human at that time, right? So people again started around that time that, okay, something is coming up. But real breakthrough came in around 2012. What happened was there are several names over here, but I will just give you some names which you can just as a backstory. In 2012, there is a professor in Stanford her name is Fei-Fei Li. She's a professor of computer science and machine learning at Stanford. She created a database, and the database had, I don't know, 100,000 images, like 1 lakh, what we call 100,000 images. Okay. And these images are divided into 1,000 classes. Class means, now you know the binary class is yes or no, right? So 1,000 classes, that means they may have cat images out of this 1 lakh. They may have dog images. They may have elephant. They may have chair. They may have table. They may have human, right? So these are one class. This cat is one class. Dog is one class, right? So she has an image, annotated image. Annotated means what? Where X is also present and Y is also labeled data. Okay, labeled data was present. So what essentially is that she has a collection of 100,000 images, digital images, all sanitized in a fixed length and breadth pixels. Okay, and their labels are also available, and those labels are spread across 1,000 classes. Okay, so this data set is very famous. People still work on it. ImageNet. This is called ImageNet data set. Okay, and we'll learn about these things. This ImageNet dataset in 2012 or 2010, from there onwards, or 2009, she started a competition, which was called ImageNet Challenge. What this competition is, that in people from industry and academia, they started participating in that, and they said that let's try to see what is the accuracy which you are getting in identifying the class. So this is a classification problem, multi-class classification problem, right? 1,000 classes are there, 100,000 observations are there, right? Multi-class classification. So write some algorithm to do this multi-class classification, especially on image data. Okay, so image detection. A lot of people from 2009, 2010, 11, they did that, and their accuracy was like 70s, 80s, or whatever, right? In 2012, Jeffrey Hinton, his group participated in that, right, in that challenge. And one of his PhD student, I think, named Alex or something, he created something which is called AlexNet, nothing but a deep learning model, right? And he submitted. He won by far. Before that, what people were using over here for ImageNet challenge was something like mostly what they were using was your either random forest or SVM, or in some sense they were using combination of these, right? Combination of these, right? So mostly falling on what side? On classical machine learning side. This is the first time when in 2012 AlexNet, or the people from his group, right, won this challenge, ImageNet challenge, using deep learning. So they use deep learning to do a multi-class classification, to solve a multi-class classification data set. And the difference between the first and the second was very huge. So people start taking notice after 2012 that, okay, they are onto something, right? This is something. Around that time itself, if you would notice, then Google Photos and all came, and then you started auto tagging of Google Photos, and Google started doing suggestions, Google started doing translations, right? All these things started around the same time because there were new interest in behind the scene around deep learning, right? People started working on something which is called artificial neural network, and that solved a lot of speech related data, text related data, your image related data. They started solving this. Okay, and then there were renewed interest. I don't know if ImageNet challenge is still going on, but this problem has been solved. Like now the accuracy is probably like 97 or 99% or something, where the human level, like if the human has to separate this, human was getting accuracy of 95%. In this, machines have surpassed human level, right? And has gone to 97 or 98%. So our goal is always to surpass human, right? Surpass human by a margin, so that we can show the benefit of machine learning or AI. Okay. This is a little bit of background just to give you, like, keep you in mind that this is how this whole thing originated. Any question?
So, Anas, like apart from this classical machine learning model and then deep learning, is there anything more advanced than deep learning in today's world? Like on which work is currently going on, or
Yes and no. They are type of deep learning models, right? So nothing which is yeah. Okay. So here is the thing, right? Whenever and wherever, in my opinion, and I have seen a lot of literature also, this AI will have the same impact. What is the impact, like how electricity has on human civilization, or internet or iPhone had on human civilization? If you notice, or nuclear reactions, right? Like these are the technologies which were evolved over time, which really changed the face of the earth, right?
correct?
Electricity, like, you can you imagine a world without electricity now? No, right? Whenever and wherever AI will start having that level of impact, right? It is still having impact, right? Our recommendations of Netflix and Amazon and a lot of things which happens through machine learning, right? All these are good, but are these impact on the scale, on the same scale what mobile phone has? Maybe not, right? Not true. Whenever that happens will only when we'll have something called robots, right? When when we'll have humanoid robots or non-humanoid robots, but they start interacting with us in a physical world, right? They will come out from the computer systems. When the AI comes out from the computer systems, start interacting with us, right? Alexa does that, but does the Alexa do make tea for you? No. Does it do household chores for you? No, right? So in my opinion, I think there are a lot of companies which are working on this, solving this problem, and it's a hard problem to solve, right? So what they are targeting is something called AGI. I talked about this, right? Artificial General Intelligence. Artificial General Intelligence is that, okay, we have been hearing from 90s that Deep Blue of IBM beat Kasparov or Karpov of world chess grandmasters and all those things, right? But the Deep Blue was doing only one and one thing, right? Even now, in a very narrow field, what we call as ANI, artificial narrow intelligence, machines have surpassed humans. Machines have surpassed humans by leaps and bounds, right? You take any field, and if you train machine enough, it will surpass. But that same machine will not be able to do XYZ things also, right? So the idea behind AGI was that, okay, you do not have to be master in all, but a jack of all trades, right? Like you should have something where you should be able to do A also relatively well, B also relatively well, C also relatively well. So more most scientists have the consensus that AGI is like an average high school or college kid, right? The intelligence of an average high school or college kid. If you achieve that through a machine, we'll call it that we achieve AGI. What AGI, like an AGI put inside the robots, will really be path breaking. So companies like Tesla, Google, Meta, I'm sure that they are all working, and most of the defense, right? Like we are always forgetting most of these research, right? The research which is being driven by the country's defense, they are always sort of not open to the public, right? So there will be a lot of research which would be going on over there also. But in my opinion, that when the robots start working in the physical form, right? At that time, with an AGI, at that time, it will be like electricity, and probably it will have impact more than that. Think about it, like if you have a relatively cheap assistant, right, who can do all the work for you, probably humans would not be doing work, right? They will become more lazier than what they are. But those are the things, and especially coming back to your question there about the technology, that will be reinforcement learning. So even now in deep learning, we have the reinforcement deep learning also, a portion of that, right? But most of these robots, the way they are trained through something called reinforcement learning. You have heard about this OpenAI and ChatGPT. A portion of that is also reinforcement learning over there. Not entirely. Most of them is supervised deep learning problem. Supervised deep learning problem. But a small like part of training, maybe we'll see that is also reinforcement learning. So if something new is coming, I would say that these are the things. At defense, nobody knows that what Pentagon is working on, or like our Chinese military is working on. We don't know that, right? They will be working on something very different. But what organization would be working is trying to crack. Tesla is working on something called Optimus, I think. It's a they were doing a project, I do not know. Like it's very difficult problem to solve. One thing is that have an AI or a chat GPT like inside the computer who will not harm humans, right? But to put something out in the world, um, who will have an intelligence of a human being and who can do work for you and move physically, right? It can actually harm you, right? In some sense. So I think those are the things we'll see in 5, 10, I don't know, 15 years. Somewhere there we'll see that. Till that time, we should be happy with whatever OpenAI is giving to us, or Google, Bard, or Microsoft is giving to us. Probably those are the things which are cutting edge for now. Okay. Does that answer your question, Krishna?
Yeah, yes, sir.
Okay. Any other question before we actually move on to deep learning?
No, sir.
Okay, let's see. So this we have already known that artificial intelligence is the overall arching term, right? And inside that we have machine learning, and we sort of again went inside that, and which is deep learning, and anything which has to do with neural network, and we'll just come in a minute that what is neuron and neural network is referred as deep learning. Okay, what is deep in deep learning, why it is so called deep, is it philosophical or not, we will also know. But this portion which is seeing in blue, now this is more like classical machine learning, right? So the probably the best model in classical machine learning, XGBoost, right? The boosting, one of the extreme gradient boosting, we have gone through that, is XGBoost, right? That comes performance wise closer, can't beat deep learning. But deep learning since 2012, as I was saying, is the reigning champion, right? You give a problem, and that problem will be solved better than anything else using deep learning. Then why people are not doing that? Like, if you ask me, in industry, probably 80% of the work is still being done on classical machine learning, and only 20% work would be on deep learning side, right? And this spread is there, right? Why? Because there is a phrase in English, right? Don't bring gun to a knife fight, right? What essentially I'm trying to say that the problem which can easily be solved with machine learning, classical machine learning, why you have to use deep learning? But because there are two shortcomings, main shortcomings of deep learning. You need a lot of compute, you need a lot of data. Compute and data both are money, right? They're dollars, they're rupees, right? It needs a lot of money. This guy is relatively easy and cheaper to cook up, right? You can do it on your laptop. The second thing is machine learning, classical machine learning works very well with your tabular data, like the table related, the database related data, right? What you can store in a pandas data frame, right? The Excel sheet, all those things, right? Works very well over there. Where deep learning comes, if you have image data, if you have speech data, if you have text data, if you have video data, right? Unstructured data, that's where deep learning flourishes, right? But if you are solving these type of problems, be ready to cough up a lot of money, right? Because these are very heavy, like image, you know, right? I showed you one time that each pixel is a feature, right? Each pixel is a feature. If each pixel is a feature and you have, can one, Akhil, your camera phone, how many megapixel it is? Do you know?
60%.
64 megapixel. What does it mean? Mega is what? 10 to the power 6, right? If I'm not wrong. 64 into 10 to the power 6 pixels is there. And if you take a square root of that, right? That means if it's a square picture, okay, then these many pixels are there. So it's a square root will be like what? Maybe, okay, forget about the length and breadth, whatever that comes. These many features are there. We are not talking about 5 feature, 10 feature, 20 feature. We are talking the features in terms of lakhs and hundred thousands and millions, right, over here. So when you are pushing the data, each picture, like Akhil took a picture of a dog and he want to have a classification using deep learning. How many features he is sending? He is sending these many features to that, and to process those many features needs a lot of compute. That compute translates to dollar. That's why deep learning had some challenges, right? But the companies which are very, very powerful and have a lot of money, they will keep doing research on that, right? And they will keep, like OpenAI, Google, and Meta, and all those people, they can throw that. And somehow you may have seen that to train a large language model like GPT-3 or GPT-4, it takes in the factor of $10 million and above, right? Probably $100 million and all it takes, right? So why it takes so much of money, right? Because it needs to process so many data and it needs so many GPUs. GPUs are not cheaper, okay? NVIDIA shares are telling that. Okay, So this is what deep learning is about. Okay, we talked a little bit, but this was the problem for Professor Yann LeCun, right? And we'll start from there. These are handwritten digits and taken a picture of it, right? Slightly pixelated, but you know what pixel is, right? So each of these images is written as 504. What is this this digit, Akhil?
9.
9. You do not have any difficulty in reading this as a 9, right? And this as a 2, right? We humans are very, very, like our brains are magical components. We do not have any problem in reading this. Okay. Now see this example. What is this, Akhil?
5, sir.
5. What is this?
5.
Again a 5.
5.
How different is this 5 from this 5? Very different, right? But humans, like we do not have any problem in identifying that these are 2 or both 5s, right? So our human biological network is trained for years, right? Years and years to identify that people can write 5 like this also, or 5 like this also, or 5 like this also, who have nice handwritings, right? They will write like this. So humans have no problem identifying that. But think about it. Will machine have a trouble identifying these? Because they are very different from each other, right? They are very different from. This is also 1. Slanting is also 1. Straight is also 1, right? People do not have identified. This is also 3. This is also 3. But think about from a machine perspective, right? When machine will see, they will see this 3 as a set of pixels, right? Or this 5 as a set of pixels, right? And all these pixels will have their brightness level. If it's a grayscale image, what is that? You remember 0 to 255, right? That is the brightness level. So 0 being white and 255 being the darker, or vice versa, I forgot. But it's a scale of brightness which will show. So each of these pixels will show you, like maybe this figure will be 64, this will be 72, and how relatively bright it is. So all these sections, right, which are in the darker, will have closer to 0, 0, 0, 0, 0. Only these sections will have some values, right? Only this portion will have some values, okay, between 0 to 255. Now, this 5, for this 5 and this 5, the pixels which are bright, the pixels which are bright will be very different from this to this, right? The pixels will be very different. Probably here, in this particular picture, this region will be more bright, right? For this region probably will be more bright, or the pixels which are brighter will be concentrated here, right? But we humans do not have any qualms in reading it correctly. For machine, it's not such an easy task. Human brains made of nearly 100 billion neurons. And these 100 billion neurons are connected among themselves with 100 trillion connections. Okay, what is a neuron? A biological neuron looks like that. Okay, so what we have is the central body part, which call it axon. We have a head, sort of, and these are dendrites. What it does is, think it like this, that this particular is a whole neuron. These are synaptic terminals. This thing gets connected to one of these things, not like a feedback, but think of 100 billion such things joined together in a mesh, right? This is connected to another neuron, this is connected to another neuron, this is connected to another neuron, and this is connected, and this is connected, and everything is connected in a mesh. Okay, so this is a biological neuron. Initially, scientists thought that they will create something in artificial world with a biological neuron. By now, people have understood this biological neuron is way too complex, right, for us to imitate. What we are doing as an artificial neuron is taking an inspiration, but artificial neuron is nowhere near biological neuron. Biological neuron, the neuroscientists have still not completely figured out that how our brain works. If you ask a neuroscientist 5 questions or 10 questions, let's say, out of 10, 8, he will definitely say that he doesn't know the answer. That less we know about human brains till now, right? It's one of the most amazing complex things which either evolution or God, whatever you believe in, has given to us. Okay. But we have taken inspiration from here. What happens over here, these connections which we are seeing, 100 trillion connections, we are referring to these connections, right? These connections over here. And these connections happen through chemical and electrical impulses, right? Or pulses. So we know sometimes you know that, okay, sodium and potassium, they are very important. They are electrolytes and they're very important for our body and all. They're important for most of the body functions, including brain, right? Because all these flow of information which happens from one neuron to another neuron happens through electrolytes, right? Like these chemicals, and through electrical pulses also. That's why the human brain consumes like 80% of our, I don't know, maybe, but very relatively very high number of energy goes to human brains because it has to work. Okay. So this is human brain, 100 billion neurons and 100 trillion connections. Now, keep these figures in mind for now. And when you say OpenAI, okay, let me just show that. Maybe that will be interesting to see. GPT-3 model. $1.5 trillion neurons. Okay. GPT-3 released in December 2020, and it has these many parameters. We'll talk about parameters also, that what is parameters, but think about how many neurons GPT is using, which is powering your ChatGPT. Okay. So these are, just to give you on a scale, right? These are 100 billion neurons, and human brains are capable of generating ideas, generating thoughts, which probably machines are still not able to do. And it is relatively very small, takes very less amount of power, right? Human brain is not like a power guzzler, right? Like they do not take entire city worth of megawatts. No, like our brains will fry then, right? It takes probably some, I don't know, like milliwatt or something of energy, right? In that. And it is able to cook up all these things, which takes probably 175 trillion or whatever the ChatGPT or GPT is taking, right? So, long story short, taken inspiration from here. But if somebody says that they are related, they are not related. They are like chalk and cheese, very different things. Okay. So we come to something called, that was biological. They take the inspiration from here, but this is how our simplified version of artificial neural network looks like. Okay. We have something which is called input. We'll go in detail that how it is, but just to make it understand you with respect to biological neuron, these are the inputs. In case of biological neuron, can you tell me what would be the input? In case of biological neuron, what would be the input? Where the input comes from for biological neurons?
All our sensory organs.
All our sensory organs, right? Mostly visual,
Yeah.
right? Because you have to process, like each second you are opening your eyes, can you imagine how many megapixels you are consuming, right? And it has to be processed because you can't send like Akhil's phone 60 megapixels image every second or every frame, right? In a second, probably how many frames it is sending. So it can't send that. So it has very optimized algorithm. And that's why human brains, right? We only pay attention to something which is moving, right? We know that which thing, if you're looking at a landscape, Krishna, like on a hill or something, do you pay or do you concentrate on everything which is out there? No. You concentrate on something which interests you, right? Maybe a tiger is moving in a jungle. That will be the focus area. Rest all the trees, all the birds, you do not pay attention to, right? So human brains is highly optimized. Probably we do not know the answer, or the neuroscientists probably something they know. I do not know those answers, that how it works and all, the vision. But it's a very complex system. So those are the sensory organs, are our inputs. Here, the inputs are Akhil's camera. Akhil's camera, right? And he was 64 megapixels. That means each image, this is one feature, this is another feature, this is another feature. So how many? 64 into 10 to the power 6 input is needed to send one image from Akhil's camera to this neural network, right? This is how it works. Then we have something called hidden layers. Hidden layers, there is nothing hidden over there. It's just that anything between input and output is a hidden layer. Hidden in the sense that output also we see, we take output like whatever. If let's say it is a classification problem, I was saying that let's say this is an ImageNet challenge. ImageNet challenge has how many classes? 1,000 classes. Each class is cat, dog, human, chair, car, all those things. So these outputs will be like multi-class classification, let's say. So this is this. If this is 1 and rest all are zeros, that and this represents cat, that means the image which Akhil's camera had supplied is a cat. Okay. If this thing is 1, rest all are zeros, and this thing is this particular neuron, output neuron, represents a dog, and this is the way we have trained it, then that Akhil camera's image, which was 64 into 10 to the power 6 pixels or neurons which were sent, they represent a dog over here. Okay, we'll come to that, how it is trained and all. But this in a nutshell is, and few nomenclatures, these are hidden layers, nothing hidden about it. This is output layer, where we are seeing the whether it's a regression or classification problem. In classification, we'll see it like this. In regression, what we'll see? Krishna, if it's a regression problem, what we'll see over here? Will we see 1, 0?
So we'll see a continuous.
We'll see a continuous number, right? We'll see a continuous variable. So let's say instead of Akhil taking a picture, Akhil is taking a picture of a houses. Okay, Akhil is going around his neighborhood and taking picture of houses. Hopefully, Akhil doesn't get beaten by that, by the neighbors, but let's say he's taking picture of houses. And he's again sending it to his neural network. And this picture predicts, the first one predicts a price. The first neuron predicts a price. The second neuron, let's say, predicts a square footage. Okay. The third neuron, or like you can imagine that number of features which it can predict. So the price will be a continuous variable, right? It will not be 0, 1. So the image, a picture is given to a, and neural network will predict the prices. That becomes a regression problem, right? A continuous variable will come. Not necessarily, till now we have seen that one output of a regression. No, not necessarily. It can have multiple outputs. So multiple continuous variable is also possible to come out. You should think artificial neural network as a mapping machine. You feed some input and you get some output. Input dictated by you, mostly unstructured like image speech type of system. Output, whatever you want it to be. Whatever you want it, like how you train it to be, what labels you have. So for training, Akhil would have to supply maybe 1 million images of house picture and their prices, right? This is the house, it is worth this crore or this lakh, right? He has to supply to train that. And then the way he has trained that, he has sent this and he has sent that, okay, maybe Y is given 1 lakh rupees, 1 lakh is not the right, this house is worth 10 lakh rupees. So it will calculate loss. How we calculated in all our classical machine learning losses, will calculate loss also over here, because this is a supervised learning problem. While training, we need annotated data, we need labeled data. Okay. The only difference is, in this particular case, it can work very well with tabular data also. But for tabular data, we have a lot of frameworks also already available. for non-tabular, unstructured data, which is mostly in the world, right? Text, video, images, speech. We use artificial neural network. Now comes the question that what is deep in deep learning, right? So this is a fancy term. This deep is nothing philosophical. This represents how many network you have, like the hidden layer you have. So people create like probably 100, 200, 5,000. Like they can keep creating these hidden layers, more and more hidden layers. The more hidden layer you create, more power you are giving to neural network to accurately identify these things, right? Whether it's a classification or a regression problem, you are giving more ammunition to your artificial neural network so that it can behave well. But what is the downside of having more layers? More compute, more dollars. So this deep represents, this is the deep part of deep learning. Okay. What is learning? Like in classical machine learning, this is also. So for that, all these layers are learning something. All these layers are learning something, right? Because during the training time, it is learning. And in the prediction time, it is predicting. Whatever it has learned, these neurons have learned, it will behave that way, whatever you have trained it on. And then, so that's the part of deep learning, right? The why it is called deep. If somebody asks you what is deep, it is the deep layer of neuron. If each neuron is connected to each of the other neurons in the successive layers, it is called dense network. Dense. Why dense? Simple, right? Everything is connected to everything. So my first pixel from Akhil's phone, and if I have, let's say, for example's sake, in my layer 1, only 3 neurons like this, then this goes here. This also sends signal here. This also sends signal here. Okay. Similarly, the second pixel also sends here, here, here. Third, here, here, here. If every neuron from a previous layer is connected to every neuron in the next layer, it is called dense network, right? We'll see all about that, but these are some jargons, like these are the nomenclatures which you should keep in mind. Make sense? Any question?
So Anas, like these layers, okay, like in what are these layers like consist of?
We'll come to that.
Okay.
These are layers made of neurons. Made of neurons. What neurons? Artificial neurons, not biological neurons, artificial neurons. What an artificial neuron is, we'll discuss.
So
Okay.
I mean to say, like by seeing this image, like if in ANN, like all data is available to all layers. Is
Not
this
necessarily. In dense network, it will be.
okay?
But nobody stops you. Like that everything should be connected to everything. Maybe this only goes here, here, and not to here. That's fine.
Okay.
Okay, that's fine. That can also be an architecture. But in a dense network, what we say is that everything is connected to everything. Like not this layer is connected to this layer. I'm saying that successive layers are, all the neurons are connected to each of the other neuron from the previous layer, right? So if I'm saying dense, that means this thing is connected to this, all these guys also. Okay. This is dense network.
Sir,
Hmm.
this is neural network with supervised approach, right, sir?
Correct.
How unsupervised approach
That will
will
come.
work?
Like that will let me first finish the supervised one, because this is the reinforcement, and the unsupervised part of that is probably is there. There are ways, like at this moment, let's park that question for now. Okay. Let's concentrate on the supervised problem for now. Okay.
Which is being widely used, sir?
Supervised problems.
Okay, sir.
This is what we are going to talk is the most widely used, right? The supervised neural network techniques, right? There will be reinforcement, there will be unsupervised also, but most widely used, because see, in real world, what we try to do always is we are interested in inference and predictions, right?
Yes.
This is what humans are like. Okay, give me something, tell me that where the stock is going tomorrow, right? Tell me that, right? Tell me where the house prices are, right? These are the problems which people are interested. Show me some movie which is very interesting, which I've already watched, right? Like not watched, right? These are the problems people are interested in. So most of these type of problems, and including your GPTs, right? Or your chat GPT, is a supervised learning problem.
Okay.
Reinforcement and all will come mostly on the either on the game playing side or the robot side, on those things. Unsupervised learning also is unsupervised, and then you push it to supervised learning problem. Okay, like how we have seen in classical machine learning, you have seen the dimensionality reduction, for example. Does it solve any purpose in itself? It is more like a dimensionality reduction is more used as a first step before you put a supervised learning, right? Because you have so many dimensions, you can't handle that. Let me reduce it and then push it to supervised problem, right? In industry, it will be used like that, right? So if you see your chat GPT and all, they're all built on supervised neural network problem. But having said that, it's not like that unsupervised or enforcement is not there. It is there. It's slightly more complicated than what the supervised problem is. So in this particular case, if you have heard about autoencoders, let's say, right? GANs, like generative adversarial networks and all, right? Those are unsupervised neural network techniques, right? But again, those will not make sense, right? We have to take a step by step. There are use cases. To give you a use case is that a very quick example. This was a picture, right, of Akhil. This is a picture of Akhil, right? And suppose you have to, one way, like zip. What does zip do? Like zip does it, like it makes the picture in such a way that it reduces the size. And when you unzip it, again, it retains the original picture, right? If you do that. So it's a lossless compression. It's a compression technique, but it is lossless in the sense that it compresses, but when you expand, it comes back to the same level, right? Or the same picture. In artificial neural network, and especially in the unsupervised, what they do is they also do compression, but they do a lossy compression. So they seem like, you can think it like dimensionality reduction, right? So they're taking, let's say this was 64 megapixel camera. They reduce it to, and that image to maybe 16 megapixel, okay? Through some technique, unsupervised technique, they reduce it, okay? The way they, now in neural network, the way they train that this particular thing should be mapped to a 16 megapixel and still represent Akhil's photo is through an unsupervised problem. Okay, we'll see that when we are dealing with maybe autoencoder or GANs, right, at that time. Okay, but keep in mind that there are use cases over here. Let's learn for supervised problem. Okay.
Yes, sir.
Okay. So why DL when we have classical ML, right? I think I answered this little bit, but let's solidify our understanding that for once and all, that why deep learning is needed, right? Let's say you are a doctor. And again, I'm picking on Akhil. Akhil is the junior most, right? So I can pick on him. Let's say Dr. Akhil, MD, is there. Okay. And he goes to his clinic and he has a lot of patients and all. And what he has to do is to identify the patients who has TB or not TB, right? So he has to see the patients who has tuberculosis. It's a disease related to the lungs, and he has tuberculosis and all. What Dr. Akhil will do? Dr. Akhil will do that. He will create a probably Excel sheet or chart or something, and he will start noting down all the parameters for the, like maybe 100 parameters for each of the patients, right? We'll do 100 parameters. And Dr. Akhil is intelligent. He knows machine learning also. He'll say that I'm noting down all, right? That whatever their pulmonary action or lung action, some features. These features are like very trivial, like whether allergy is there or medication is there or what is the gender. But he will take like lungs related data also. So all the tabular data will be there. All the tabular data. Let's say he has taken 100 features for each of the patients. and he has got 1,000 patients, let's say. And Dr. Akhil knows machine learning, right? What he will do? He will create a classical machine learning problem, right? He will do his feature engineering, he will do his data cleansing, he will do his EDA, all those things he will do, right? Right or not? He will do that. And then he will come up with, he will train probably 4 or 5 models. He will do his boosting, decision tree, random forest, all those things he will do, right? And some sort of aggregation also he will do. Okay. And then he will come up with a model. And the model, what it will do? It will predict TB or no TB, right? A classifier. He will put a classifier, right? This is one way of doing things, isn't it? This is one way of doing things, and it's a very good way of doing things. That whether some person, Dr. Akhil identifies the person has a TB or not TB. Okay, fine. The second way is this way. The patient just comes with a scan, X-ray, and through an X-ray, let's say you are able to identify, the doctors can identify TB or no TB, right? Looking at the X-ray, some portions dark or red or whatever, right? I do not know, I'm not a doctor, but looking at the image, they can see that. Now, Dr. Akhil has learned recently deep learning also. He said that, oh, I'm not going to do all this nonsense over here, right? What I will do is, I have this image, I will train a neural network. Okay, let neural network figure out whether the person with this image has a TB or not. All I need is probably I have a image database of 1 million or maybe 1 million X-ray images. And these are annotated or these are labeled TB or no TB. If I have access to that, what I will do is I will train my artificial neural network, right? Or a DL model. I will train that. And I will train it in such a model. After training, I will just supply the image to that model. This is my ANN model. I'll just supply image and it will give me 0, 1. That's it. Like, I do not need to capture, I do not need to know that what is the patient history. I do not need to know what is the gender, what allergy is there. No, nothing of that sort I need to know. All I need is the image. And this image will tell me the story that whether the person has a TB or not TB. Okay. This is another approach of doing it. You got that, right, Akhil? That there are 2 approaches can happen like this.
Yes, sir.
Right. Now, what is the difference between these 2 approaches? Main difference between this approach and this, we know that this is tabular data, classical machine learning, and this is an image data, unstructured, feeding it through the neural network. But what is the difference between these 2? Like, can you tell me that some difference, right? What is the difference? What we are doing differently here? Like, which is more
Yeah.
much, which is will feel me more easier, which will give you less pain.
Tabular data, sir.
Tabular data will give you a lot less pain, right? Because
Yes,
you have
sir.
learned classical machine learning and you have still do not know DL. Okay.
I felt because these have less number of features than image data.
Correct. Krishna, what do you think? Like, what is the few differences between these 2 approaches?
I think as far as data is concerned, this pictorial data will give me more accurate results. But yes, computing this maybe analyzing these images will have more compute, so we'll need deep learning kind of.
Yeah, true.
Yeah, and it yes, so it will be more accurate and more easy because like only we have to collect one form of data that is X-ray of chest. Here we have to collect 100 different features like what is your BP, and so like for one patient we need to collect many parameters. And in the second one we only need to collect X-ray of their chest. So that is easy. Computationally that is maybe difficult, but like For collecting data, that is easy.
Good. Okay. Now, which will be cheaper?
Tabular.
Tabular will be cheaper. Which will need less data to train? We know that classical machine learning needs a fraction of data what the deep learning needs, right? I told you, right? So in tabular data, in classical machine learning, if you're employing, it can work well with a very small data set. Deep learning, anything less than 1 million will not cut. It will not give you good result also. Okay, or 100,000, right? But probably you can train with 1,000 observation a classical machine learning model also, and it will give you decent result. Okay, so this is like, it is cheaper, it will give you decent result. But if you want to build a very sophisticated state-of-the-art system to detect a tuberculosis, right, then this is the way to go, right? And now let's put this problem in a different spin. Let's say you are a private company. Dr. Akhil has floated a private company, and now he is from a government or something like that. And then what he does is, in rural India, there are not many people, not many trained doctors are there, but probably the government of India has installed a X-ray machine in every village healthcare system or something, right? What will happen? In this particular case, it will be much more easier, because what you will do is you will create a web app, right? How you are doing through Flask or Django. You will upload your images, scanned images, and it will give you the data. You do not have the people on the ground do not have to train 100 different features or get 100 different parameters from the people to identify that. Anybody, like a 10-year-old, a 15-year-old who knows how to play with a mobile, can download the app, scan this image, and tell you that whether the person has a TB or not, right? So it becomes very simple. But there is one more very, very critical difference between these two, which we are forgetting. What we are forgetting? What is the first, second step of a classical machine learning journey? Okay, what do we do? Like after we gather the data, what are the things which we do before we build the model? What is the thing which we do?
Sir, EDA and feature engineering.
Feature engineering, right?
Yes.
Do we need to do any feature? Do we need to do feature engineering here? Maybe these date of birth and patient names are immaterial. Maybe they are material, right? Maybe date of birth gives you the age, right?
Yes. Yes.
It gives you an age-related data. So maybe this is actually a good feature. But will this feature work? Or this has to be translated into a feature called age, right? You have to do feature engineering, right? You have to do all these EDA portion of work also. Over here, nothing. You don't have to do. As it comes, as it goes, you feed. So one of the very, very important difference between classical and deep learning is that there is no need to perform feature engineering in case of deep learning. Features are learned inside the model itself. In classical machine learning, you need to have domain experience. You need to have some sort of understanding of the problem where you do feature engineering before that. Deep learning is more like a black box. I do not know what you're doing inside, but train this. This is the data. This is the output level I want. I have a lot of images like that. I will train it. Ultimately, I hope that my loss is very less. My test and validation sets loss are okay with me. I'm not overfitting. Till that time, I'm good. Okay. That is one of the things, right? That why DL is important, right? Why we are seeing DL. No feature engineering. But there are other factors also. Let's say we are building a car detector. Like again, through camera, we are taking a picture of car and we are doing a car detector. Like everything is a car, right? If this is the orientation of car, it is still a car to human mind. If this is the orientation, it still is a car. If this is the orientation, it still it is a car. If the lighting is little less, it is still a car. If the angle is little different, it is still a car. To human mind, it is a car. But for a machine to detect it a car, is very, very difficult, because if you change the lighting, if you change the angle, the amount of pixels which is brightened or which is not bright will be very different. Their spread is very different, right? Now tell me, if you have a car detector sort of classifier, that whether the image is a car or not, is there any classical machine learning? Now you have learned classical machine. Is there any way you can devise a problem statement or a model which can detect that, right? Random forest, your boosting, XGBoost, can it detect a car? Because all the next image which you will get will be in a different light, different angle, right? Different color of the car. Everything will be different. Like, this shows the enormity of the problem, that where classical machine learning will fail. There is no way you can detect that. Why we cannot detect that? Because our data is not tabular. Our data is not consistent, right? The images, the observation, this also should be classified as a car. This also should be identified as a car. This also should be done as a car. But you change it in the daytime, the same car, same angle, daytime and nighttime, the image will be very, very different, right? Same image, same car, same angle. During day and night, it's very different. So classical machine learning fails in those kind of situations. Okay. Advantage of DL over classical ML. This is how I was taking. You have an input, you do feature extraction or feature engineering. Then you pass it to a model and you get an output. In deep learning, input, you just push it to a black box. What it does, it will do feature extraction, feature engineering, feature selection, all inside that. It will know that, okay, what to keep, what not to keep. In lung image, X-ray image, it knows what to ignore, what not to ignore. It will figure out. And then it will work as a classifier and it will give you the output cat, like car or not car, or TB or no TB, or whatever be the situation, right? So this is the main advantage of having DL. You do not need to be a domain expert in that, right? You can still do that. Okay, traditional machine learning, cat image, cat detector, handcrafted features, learned classifier. This has to be done with hand. Over here, no. These are the, let's say, these are the layers of neurons, right? These are the layers of neurons which are being passed. And this is the output neuron, right? And this is the input neuron. It will start learning the feature on its own. We do not know what it is learning. But as long as our loss are getting lower and lower and lower after successive trainings, we know that it is learning. How it is learning, what it is learning, we do not know. We have no clue about that. It is all inside the black box of neural network. And these are different layers, right? So we may think that it is learning low-level features, it is learning mid-level, high-level feature, and then it is working as a classifier. But these are all assumptions. We'll see that. So overall, whenever you have tabular data, you can work with neural networks with tabular data, but why work with neural networks? Classical machine learning will do the trick. Don't bring gun to a knife fight, okay, is the thing. Artificial neural network, which takes a lot of data, lot of compute, lot of dollar. Most of our industry data is still in tabular form, right? Customer data. Are they unstructured? No. But if you are working for Tesla, where you have doing the autonomous car and all, the images are not tabular. There is no way they are tabular, right? They are images. So if you are working with image data and those sort of problems, a type of, we'll see that what is this convolution, but a type of neural network works. If you are working with text data, again, either you do without deep learning, natural language processing, or RNN, or some sort of neural network. Let's not go with these terms. We'll see that neural networks works well, or NLP, right? Classical NLP also works well in this thing. If you have video and all, what is video? Or if you have speech and all, there is no way you can do that with the classical machine learning, right? It's very difficult problem to solve. You have to use your neural network. So whenever you say, hey Siri or okay Google and all, behind the scene, it goes to a neural network. It doesn't go to a classical machine learning to understand your text. Okay. this chart is very interesting, right? And this also says that why deep learning is becoming more and more popular. Till 2000, right? Because before the advent of the mobile phone and data and all, what was the picture data in the internet? Like there was no YouTube, probably pre-2000. There was less video. After iPhone and mobile phone camera, there was a lot of pictures which are floating around. There is social media which came after that, which is primarily photo, video driven, all those things like this. So there is a explosion of data which happened, right? But till very recently, this data was very limited in tabular nature. At that time, when people were doing the performance analysis of the data, the amount of data, your traditional machine learning like SVM or logistic regression or something which he mentioned, all these were performing on the similar level, right? There was no bonus, there was no added advantage to get that. But as and when data increases, right, the data keeps on increasing, your performance started plateauing for, let's say this performance metric is like for classification type problem is accuracy. Your accuracy will start plummeting, right? It will be plateaued for your classical machine learning. But more and more data you supply, better and better accuracy you will start getting from a neural network. And he also found the interesting thing is that larger and larger the neural network you build, more and more data you supply, the better the performance you will get. So the best thing is have a very, very large neural network, have a lot of data, and you will achieve some superhuman intelligence. And that's what we are seeing with OpenAI and all, right? This is exactly what we are seeing with the OpenAI and ChatGPT and all, right? Like, because they have been trained that your ChatGPT or assistant model, any assistant model has been trained on the entirety of internet, Wikipedia, Reddit, everything included, entirety of internet. So it has built a very, very large neural network, and it has been built on a large amount of data. And that's why the performance will be very, very high. If you are doing the traditional, even if you take the lot of data, right, but use the traditional machine learning network on a text-based data, let's say, your performance will plateau. But and when you increase the neural network size, it keep increasing, right? So the recent, again, for the sake of repeating, the recent what you are saying in 5-10 years, whatever the buzzwords are coming or the hype is getting created, it is creating because the compute is becoming relatively cheaper, or the compute is becoming available because of hyperscalers like your cloud providers. So whether it's Azure or GCP or your AWS, they are hyperscalers, and they are giving you NVIDIA GPUs as a to rent out, right? Essentially, it is renting on a subscription. They are giving you, so you can go ahead and train your model on this hyperscaler. You do not need to buy those GPUs, just costly GPUs at your end. We'll come to that how GPU is solving this problem of this performance, right? We'll park that for now, but GPUs are nothing but accelerators. It does mathematical computation very fast. We'll probably deal with that also. But for now, just assume that since we have a lot of data and we are building large, like big neural networks, we are achieving superhuman capabilities, right? Which we are seeing. One more thing before we see is neural networks in general, no need to read all these things. Neural networks in general are called universal approximators also. Just remember this word. We'll deal with that in a minute. Universal approximator. Why we call it, we'll deal it with an, I think we have a slide for that. Okay. So these are some of the things which I, as a refresher, I put it. So feature learning, not important in complex non-linear relationships, deep learning will work. Large scale data, deep learning loves that. Image and speech recognition, classical machine learning fails, deep learning. Unstructured data, same thing. Transfer learning, what is transfer learning? Transfer learning is something that you train one time and you reuse it multiple times. So what is happening in case of deep learning is, let's say, the first model of deep learning, let's say OpenAI, has trained it on entirety of internet, right? So it has a basic understanding, that model has a basic understanding of how a sentence is formed, right? Or a context of a sentence. It has the form. But what with ChatGPT, what they did was they did a fine-tuning portion of it. What is the fine-tuning portion? Fine-tuning portion that if somebody asks you a question, you respond with an answer, not with another question, okay, or not extend the question. Your GPTs were all doing where GPTs were like autocomplete. Okay, GPTs were like autocomplete. It will keep continuing the same string because on internet, whenever you read a Wikipedia article, if you save one sentence, it will give the next Wikipedia article sentence similar to that. Not exactly, but similar to that. So it was doing that. Transfer learning, coming back, is that when you put one model, okay, whatever it has learned, and then you put in somewhere else on some other machine, and you start from that point onwards, start fine-tuning from that point onward. You do not have to again fine-tune from the scratch. Why it is happening? Because all neural networks are learning. All neural networks are learning. What is neural network learning, right? To give you, let's say, this is my very basic neural network, okay? This is my very basic neural network. All it is learning, we'll see that in a minute, is that these are the, like, what is the parameters involved over here? The connection parameters. What is the value of that? Numerical value. All it is learning is that, right? So it's very easy to transform from one system to another and retain the knowledge which the model has learned, right? That is transfer learning, okay? End-to-end learning also, no need of feature engineering. You just supply everything and it will work, okay? What's the drawback? Data requirement, huge. Computational resources, huge. Interpretability. In decision tree, you can't tell that why you denied a loan. If you are building a loan application through deep learning, there is no way. Like all you will get is the model weights and biases, the model parameters. These model parameters will not tell you why a person was denied a loan or approved a loan. There is no way. Artificial neural network or deep learning is complete black box. There is no interpretability over there. That's a big challenge which industry is trying to solve. Training time takes a lot of time, takes a lot of data. Energy consumption. Obviously, when you are taking it more time, your computers are not going to run on thin air. It is going to run on fossil fuels or some sort of fuel, right? So a lot of energy consumption. This is also one of the things which people are against training large language models, because they need tons and tons of compute, and behind that tons of energy also. Okay, let's see. We'll start with, like, what today we'll do is that we'll learn the first, like, artificial neuron, how it looks, how it behaves, and the very initial type of artificial neuron is called a perceptron. So to give you some analogy, today we are going to learn A, B, C, D of, and from day onwards, we'll see that how to form the sentences after, or form words, and then we'll see how to form the sentences, right? But let's start with, these are the alphabets of deep learning, okay? And the first building block of the Lego block is perceptron. So what is a perceptron? Perceptron is a relatively simple concept. Okay. You pay attention to this particular block over here. Okay. What we are doing is, let's say, and this was done in 50s and all, right? So this is fairly old technique. What it is doing is, let's say you have 3 features. These are my features. X1, X2, X3 are my features. Okay. And probably the best would be that to understand this with an example. Let's say your X1, you are building a machine or building a neural network, a perceptron-based neural network. Will come what perceptron is, that you're building, that whether it's like a classification, whether I should go for the movie or not. Like, that is the problem, whether I should go for the movie or not. Okay. And you have 3 criteria to decide that. These 3 are your features, right? And these features are all binary. Binary means either 0 or 1. It need not be, but let's, for the example's sake, just assume that these are binary in nature. Your X1 may be something like how is the weather, right? Is it rain or no rain, right? Do you have company? Like, are you going with friend or no friend? Are you going alone? And do you have transport available? Like, do you have a car or friend has a car, or you have no transport, right? Let's say you have three features and you are trying to make a decision out of that, that whether you should go and somebody should go and watch a movie or not, right? This is the simple statement. What we are trying to do over here is these three input features we are feeding to a perceptron. We are not yet calling it neuron, and there is a reason. We are feeding it to a perceptron. What perceptron will do is, it is doing a very, very simple task. It is so simple that it will appear. Okay. So each of these edges which you see, which is connecting a input to a perceptron, these are called the weights of the system. Weights. Now, what is weight? The weight is, if you have to understand that weight, that in this particular decision, output decision, what is the contribution of feature X1? What is the contribution of rain or no rain? How much of the deciding factor, rain or no rain, is in your overall decision? That is dictated by your weight. Clear? How much the W2 will dictate that what is the percentage of weight or the percentage of contribution in your decision, that whether you have friend or no friend to go along with you. W3 will dictate that what is the contribution, that whether you have a car or a bike to go to the movie or not, right? And our overall aim over here is it should give 0 or 1, whether I should go for a movie or I should not go for a movie, right? Based on these criteria. Clear? Till here, everybody is with me? That what we are trying to do? The way it calculates from input to output is it takes a weighted sum. We all know what weighted sum is. The weighted sum is what? X1 W1, X1 into W1 plus X2 W2 plus X3 W3. This is the weighted sum. The weights multiplied by the individual features, right? The weights multiplied by the individual features. This is my weighted sum. So this particular perceptron is not doing anything, but it is taking a weighted sum over here, right? And you remember that W1, W2 are giving the relative importance of this feature in the overall decision-making process, right? And X1 is the data which you are supplying, okay? So this is how it looks. Now, there is something called B. We call it bias. Bias, you have to see it as a threshold. That if this weighted sum crosses a certain threshold, B, my decision should be that I should go for the movie. If it doesn't cross a threshold, a level, if this weighted sum doesn't cross a threshold, a level, I should say that no, I should not go for the movie. This is what it is being said. Because in machine learning and deep learning, everything is numerical, right? So whether you have friend or no friend is in 0, 1. Whether you have company or transport or no transport, it is 0, 1. Rain or no rain, it is 0, 1. Whether it is raining or not raining. Similarly, the weights are also in parameters, right? The weights are also in numerical forms, right? So, for example, this weight could be, this could be W1 could be 2, W1 could be 2, W2 could be 1, and W3 could be 3, right? So this is the relative weight. Relative weight means if it is 3 over here, what does it tell me? It tells me that transport is a deal breaker for me. It has the highest weightage. Like whether the transport is there with me or not will mostly dictate whether I go for the movie or not, right? And then I have to cross a certain threshold for me to make my decision. If, let's say, and we'll see that with an example, but for now, this is the construct of a perceptron, right? The perceptron is nothing but, in a layman terms, if you have to say, it's the weighted sum of features with weights. And if you are crossing a certain threshold, you are going or you are making a decision according to like positive class. And if it fails to cross a certain threshold, you are landing in the negative class. That's all we are doing. And mathematically, we are representing it like that. Like, let's say if it makes sense or not. It is saying that wjxj, summation of wjxj for all j's, what is it doing? This is the thing, right? Summation of wjxj for all j's. If it is less than a certain threshold, the decision should be 0. If it is more than a certain threshold, the decision should be 1. The other way to represent the same equation is like this, right? I have taken the b on the other side, right? What is this? This is the dot product. Now, why it will be a dot product? W, if W is a vector, X is a vector, then this could be a dot product. How? Let me just show you. We can represent it like this, right? True or not? This will represent the same thing as this or not. Now we know all these, hopefully we have not forgotten our linear algebra, right? Vectors and matrices. This is the dot product of these two, right? Correct? So it is being represented as the dot product of weight vector with a feature vector and added a threshold. If it is less than 0, call it 0. I'm not going to the movie. If it is more than 0, yeah, I will come for them. Or threshold weights are the relative importance. Appears greater than this, I will go. Okay. Makes sense till now? Any question?
Unless I have a question, like output
Yeah.
of output of perceptron will always be a binary output.
No,
Okay.
not necessarily, not necessarily. In this particular case, to make things easy, I'm keeping it a binary. It doesn't need to, because perceptron can give you a continuous variable also, right? So
Okay.
first we are seeing the classification side, right? Like, okay, 0 and 1. Then we'll deal. But it doesn't have to be.
So I mean to say, like we will represent a value which will be sum of all products of X and W, right? And then here we are, if that value crosses a threshold value, then we'll allot 0 or 1, right? So that will be binary output. In case of continuous, the value of B and F will
just
remain
directly, you pass it directly.
Okay.
Yeah, because we have to, what we are doing, we are converting, if you think, and that's a very good point, Krishna, we are converting this as a continuous to a discrete value, right? And from this was a continuous variable, right? To convert this to a discrete and make it 0, 1 binary classification, we are introducing something called a step function, right? That if this thing crosses B, fire it as 1. If it doesn't cross it, fire it as 0, right? You know the step functions, right? We'll just deal it in a moment. But essentially, this is the same thing which we did, if you recall long back, in case of logistic regression, right? We are passing through sigmoid function. Logistic regression was linear regression, right? We forced it through sigmoid function, right? You remember? And
yes,
the sigmoid
yes,
function was doing what? It is constricting it between 0 and 1, right?
correct.
And we are saying that, okay, if it is threshold above that, push it as 1. If it is threshold below 0.5, push it as 0, right? In logistic regression also we were doing that. So logistic regression is nothing but a perceptron. If you think that way, think through it, then this will make sense, right? There also we were doing the same technique. Here also we are doing the same technique. Okay. Any other question? So this we already dealt with, but just for the example's sake, so this will be W1x1 plus W2x2 plus W3x3. And if this thing is less than or greater than a certain constant, I'm representing it by key, but it can be other. And when you move this on the other side, what it will become? Summation Wi xi I plus b. If it is less than 0, 0. If it becomes greater than 0, it becomes fires as 1, right? All we are doing this. And now let's talk about step functions, right? I was talking about that, how this thing can be materialized. So till here, what we are doing is, we are doing the weighted sum, right? And we are adding bias term. What we are doing, we did the weighted sum and we added the bias term, right? But this particular thing, how we are evaluating is the question. So the way we'll evaluate is, let's say this is x and this is f of x, right? This is the output of that, right? So a step function is called like this. This is 1. This is 0. Okay. I'm drawing it at 0, but it need not be. So when your x, this is your, over here, in this particular constant, in this particular thing, if this is your x, and if it reaches a certain level, right, over here, what is the level? The level is if it passes more than 0, if it is becomes greater than 0. So if your fx becomes greater than 0 over here, right, what it will do? Your fx, sorry, if your x becomes greater than 0, what you do? You pass it as 1. Till that time, you pass it as 0, right? So this function will actually represent this whole thing. Make sense or not? Let me repeat that. Over here, what I'm saying is that I'm just trying to represent this particular thing, right? This particular thing through a step function, right? What is happening over here? If this thing, this whole thing is becoming greater than 0. What is this whole thing? This whole thing is becoming greater than 0, right? That's what I'm saying. If this thing is becoming greater than 0, push it at 1. If this thing is becoming less than 0, anything, any value over here also, what I will park it at? Any negative value, I'll flattening it at 0, right? Anything positive value, I'm flattening it at 1. This is called a step function, right? So if after this, we put a step function over here, our classifier becomes good, right? We should be able to do the binary classification. The same thing we were doing with sigmoid also. If we put a sigmoid over here, instead of a step, it will become like this, right? It will be slightly gradual slope like this, right? But it will still be between 0 and 1, and it will not be so drastic, right? Change like this, right? And it will become like this. We'll learn that how we can use sigmoid, but the step is the simplest. That's why you are employing step functions over here to make things simple at this moment in time. This is what a step function is. Everybody is with me, like how we are doing this, how this particular thing is calculating, working as a classifier, right? Everybody got that intuition? Because this is the basis of how a neuron works. Everything builds on top of it. Okay. Any question you should ask now?
Anas, I have one more question.
Go ahead.
Like W1, W2, W3, these weights are provided by us?
No,
Like,
these weights are learned. That's where the learning is. The learning, during the process of learning, when you are training the model, these weights will be initialized with something like random. At the beginning, you do not know what is the importance of friend versus transport versus weather. You do not know, right? Okay. There's no way of knowing, but you have historical data, right? The historical data in the sense that when Vimal was deciding for the movie in the last 1 year, this is the data point, right? And the data point will be like, in this particular case, the data point will be tabular mostly, like, so this will be like your x1, x2, x3, and your y, right? So data will be like, at that day, when he went for movie, y is equal to 1, he didn't had any friend, but the weather was good, right? That was one data point, right? Similarly, there will be other data points, right? Similar to that. And then when you feed all these observations to the model during the training, what model will learn model will learn these W1, W2, W3, and B. These are the parameters. So in OpenAI, when I searched Google that 175 billion parameters, right? It said, na, 175 billion parameters GPT-4 is trained on, right? This is one. So this perceptron is trained on 4 parameters. What are 4? W1, W2, W3, and B. These are the 4 parameters for which we are training. Compared to OpenAI GPT-4, which is trained on 175 billion parameters. Make sense?
Yes.
Okay. Any other question?
Sir, sir, here B is biased term, right, sir?
B is biased term. We call it threshold for now, that just to make you understand that what bias really means. Bias means that if you are crossing that threshold, fire as 1, classify as 1, right? So,
yeah.
But this is the bias term. Yeah, you are correct.
Sir, in the picture, why arrow marks were there inside, and why B is there inside the circle, sir?
Oh, okay. That's just a representation. Okay. So you can put B as here. It will not make any difference. And later we'll see that I think people start representing like this. It's just a representation. What it is actually telling you that this is the thing which will happen. That the summation of Wi xi plus B. This is what this whole thing is working out to be, right? Okay, you can supply it as a constant term B over here, and then take this is the weighted sum of the feature plus a threshold. Weighted sum of feature plus a threshold gives the output, right? Which is represented as it. Make sense?
Yes, sir.
Okay, correct. And then since it is a classification problem, we are passing it through a step function. Very simple. Simplest is a step function. We are passing it through that. And we are getting the binary output, since we are dealing with a binary classification problem. Okay, that's all we are doing. And W1, W2, W3, and B, these are parameters which are learned during training. That's all you need to know for now. Okay?
Yes, sir.
Okay. Yeah. So this was the step function. I think I already dealt with you, right? So this was my Z, right? When this thing crosses 0, when this thing crosses like that, this thing crosses 0, when this comes in the positive domain, right? Positive territory, right? The X becomes positive. What it will happen? Sharp jump, go to 1. Anything, if Z is less than 0, right? If Z is less than 0, or this thing is less than 0, so it may happen that it is the actual function will be something like over here, right? But no, flatten it out to 0, right? Because we want to predict 0 and 1 only. That's what we are doing. Okay. This particular thing, this particular functions, like in this particular case, we are putting a step function in front of it. After this weighted sum and adding of bias, we are adding a step function in front of it. Why we are adding a step function? So that we can get a binary classification problem, like solve. Correct? These type of step functions or any functions which you are putting in front of a neuron or perceptron is called activation. Why it is called activation? Because this is again from the neuroscience, from the brain time, right? We say that a particular neuron is fired. Fired means lighted. So a particular artificial neuron is fired, activated when using this activation function, right? It is activated using this step function, right? So that's why we call it activation function. A step function is a very small case. There could be n number of activation functions, which we'll see later, right? And why we are using different type of activation function. But the goal remains the same. After every neuron, when we are doing, or perceptron, when we are doing this weighted sum and bias, right? When we are doing this W1, W2, W3 plus B, right? When we are doing this exercise, we pass it through a activation functions, and then we get the output, right? So a neuron has 2 components. One is it does the sum, right? Weighted sum or whatever. And then it passes through an activation function, right? It has 2 jobs. It has 2 components. One which does the sum, the second which does the activation, right? Correct? Everybody with me? Okay. This is the example which we are showing, right? So weather, company, proximity. Okay, there is no transport, but yeah, let's say this is proximity. How near are they? Let's say, for example, like just to see it, this, and this is activation, right? When it will fire up or not. And my bias term is -5. This is like the learned, like the model is not trained, right? If the weather is 0, if the company is 1, if the proximity is 1, what will be the value? 0 into 4 plus 1 into 2 plus 1 into 2 minus 5. True or not? This will be the value. This will be the model will interpret. That means this becomes 0 plus 2 plus 2 minus 5, which is equal to -1. It is still negative. And if I have put a step function over here, whether it will fire or not, my z is -1. What will be my y, like the output? The output will not fire. It will be 0, right? Because it is a step function. Anything negative z, that is what? -1. It is at -1, right? It will not fire. It will flatten out at 0, right? So no activation. What does it literally mean? It literally means that weather is a very heavy parameter for me. It's a deal breaker for me. If it's rainy, I do not want to go, right? That's what it means. Because 2 were fired up, company was positive, proximity was 1-1. But still, even if I have friends, even if the movie theater is nearby, if the weather is not good, I am not going. This is the rule-making thing which is you are seeing in form of a perceptron, right? True or not? Let's see another example. If the weather is this time good, not rainy, and the movie is far, but you have friend, what is happening? 1 into 4 plus 1 into 2 plus 0 into 2 minus 5, right? This becomes 4 plus 2 plus 0 minus 5, which becomes overall 1. If it becomes 1, a positive quantity greater than 0, what it will do? The step function will fire, right? It will give the output 1. True? That means this whole perceptron, whatever it has learned that as long as weather is good and any of these things is okay, one of these is working in my favor, I will go for the movie. So either if the company is good or I have friends, or if the movie theater is near, either one of them is good, I will go. But weather is a deal breaker for me, right? This is what ultimately, if you try to write it into an English paragraph, this is how you will write. True or not? So this is a concept of perceptron. This is what the perceptron. It's a simple logic getting codified in mathematical language, right? That's what it is. Okay. Any question till now? We just saw the example with a working example, right?
Sir, how can we validate this?
How can we validate this? Okay. So how do we validate any machine learning problem? You tell me, Akhil. How do we validate?
Like evaluation metrics like precision rate.
Yeah, exactly. We'll do that for neural networks also. Neural networks are no different. It's a machine learning problem itself, right? So there will be a loss function. You remember from simple linear regression or any other classical, there was a loss function, right? When we are training, we are trying to minimize the loss, right? Not go in overfitting region. We have to reduce the bias also. All these things will do. It's just that we are not using an algorithm here. We are using neural networks here. So not like decision tree or random forest or boosting or gradient or none of those things we are doing. We are building these perceptrons, and we'll build a connections of perceptrons, dense connection of perceptrons, right? And with some activation functions thrown in. And we'll assume that once we train this, when we are training, we are supplying these, and we have labeled historical data, right? We'll compare these two. What I'm supplying, what should be you remember these things, that there will be, just a minute. This thing has stopped working for some reason. You remember that y hat and like the observed yi minus y hat, right? That was the residue or the loss we were calling, and then the RMSE, the root mean square loss, when we do the yi minus y hat the whole square, that was the RMSE loss, right? All those techniques are still valid over here also. We'll calculate the loss. How we'll calculate the loss? Let's say in this particular case, these are the data sets which are available to you. Let's say this is the data set which is available to you. Okay. You have y variable, you have inputs, right? And let's say the prediction is you have 1,000 such observations or million such observations. What you will do? You have y and you have y hat also, like what it predicted, right? Then what you will do in case of regression, you used to take RMSE loss, right? Now you tell me in logistic regression, what loss we took? It was 1 0 1 0 1 0 0 1, right? They were separate, right? Binary cross entropy loss. We took that, right? Here also we will take the loss. If it's a regression problem, we'll take probably RMSE loss or some other loss. And then we'll try to minimize that loss somehow. Minimize the loss, including seeing that it is not going in the overfitting region. Once the loss is minimal, we'll say that our model parameters are trained. Our model is trained. When we say model is trained, what we actually mean? We mean that W1, W2, W3B I have arrived. I have got my appropriate level of W1, W2, W3B. Now, in case of prediction time, in case of production time, what we'll do? I'll supply X1, X2, X3. Okay? From the learned W1, W2, W3, and WB, it will give a prediction. That will be my validation or test prediction, right? Then again, through cross-validation technique, all those, whatever you have learned are going to be utilized here also. Okay. So we'll see that our validation, if your training loss was very low and your validation or test loss is very high, what does it tell you? That you are overfitting, right? You have to do something else. If the training loss and test loss or validation loss on a similar range, I said that it's fine. I'll put it in production. Let it do. Okay. How you, like, what are the other things? There we are doing feature engineering also. Here we are not doing feature engineering. Here, what are the important things which we have to figure out? Important things we have to figure out is that how dense the network will be. How many layers of network we have to make. How many layers we have to make. Apart from that, each layer, how many neurons will be there? What sort of activation function I have to use for each neuron? These are the hyperparameters which you have to deal with now in this particular case. Okay?
Okay.
Okay. I think we ran out of time. Okay, we'll resume our class from here tomorrow. Okay? We'll complete perceptron and we'll go to artificial neural network. From there, we'll talk about activation, how to build a fully connected dense network. And if time permits, tomorrow itself we'll see we'll see some code, right? How to code a neural network, right? A basic neural network. Maybe we'll try to see that how to read these digits, right? Handwritten digits. How to read that. MNIST data, that is called MNIST data, but how to read that digits and how to build a classifier out of it. Multi-class classification. And what is the framework which we use? Remember, in all our classical machine learning, we were completely on NumPy, Pandas, and we were on scikit-learn. Here, NumPy, Pandas will be there, but we'll go on to where? Keras and TensorFlow. These are the framework. TensorFlow is from Google. Keras is a simpler alternative, not alternative, abstraction built on top of TensorFlow, right? So that we can easily put our or easily make our neural networks, right? So we'll mostly be dealing with TensorFlow and Keras framework, not scikit-learn. Scikit-learn is not for deep learning. Okay. So we'll move on from scikit-learn to Keras and TensorFlow, but that we'll see in coming weeks. Okay. Okay.